Okay, so we will do 3 things today in 3 parts, and you can remind me to stop a little bit after the third part. The third part will be the fun part where we will bring up the animations from this public website and look at some of the molecular motions. But I wanted to continue with, so let me start by calling it regular representations or regular permutations. So this actually I personally find it a little difficult to register things. Just because you call something regular doesn't suggest any property, but you just think about it and see why this is important. So this has to do with embedding of the group of order n into Sn. Okay. We said that this was a homomorphism. Remember, we can map the elements of any group of order n into the large permutation group Sn. So it concerns the embedding of G equal to n into Sn, the symmetric group of order n, the permutation group. So what does it concern? So remember the properties. So recall how we do this map. Can be constructed for G belonging to G, and the process was, look at the multiplication table. So we look at this table, which will look something like this: E, A, B, dot, dot, dot. And then there will be some element called C. So here some dot, dot, dot. C, which of course under identity will remain C, and then begins to do something to this. So I'll just write C times A, C times B, dot, dot. That's what it does, right? It's a product of C and B, that row. C and A, C and B. So we are looking at and it can continue of course below. Now the way to construct pi of C is simply to first fill the, thank you, just for change of color. What we will do is write the top line to be this. We simply write out the unaffected ordering of elements here, and then pick the line corresponding to the multiplication table, corresponding to the row of the element C in the multiplication table, and put it as the second line. That's all you have to do. Okay. So it will become C, CA, CB, etc. Of course, we are writing a composite symbol, it will become a single symbol once you know what it is. So the point is that essentially the element is constructed by lifting the row out of the multiplication table. This endows this particular element of Sn with certain properties which are special. What is special is that if you have a very general Sn element, there may well be lot of elements which are not touched, right. If I have permutation group of 15 elements, a particular permutation may affect only the first 10 and not affect the others. So things like that are possible in a Sn group. So it is affecting only some subclass of the elements in that group. But when we are looking at this particular subgroup of Sn, every single element n is always touched because of the group property of G. So due to Sn can be thought of as containing, okay, contains two kinds of elements. We define what kind? One where all n objects have to be changed or transformed, and one where some subset of, this is the carrier space we are talking about. So some subset of the carrier space n remains unaffected. So what we observe is that our attempt to represent a specific group of order n into Sn necessarily brings out those elements from Sn where all elements have to be necessarily touched. The embedding pi of G necessarily contains category 1. So let us call this category 1 and category 2. Okay. Do we agree with this? This is because you remember that if you have a group multiplication table of n order, group of order n, then any row of this has to necessarily shift things around. It cannot say, it cannot give C times B equal to B, because then C would be identity element. So if C is a non-trivial element, its multiplication with E will be itself, and it is necessarily going to change every other element into some other element. And therefore, this kind of permutation necessarily has all the elements changed, all the n elements. Sn is some, so n elements of the carrier space on which you are doing the operations. So the big group Sn therefore can contain large number of elements you are not interested in, where some subset of n remains unaffected. In fact, those will be elements of S sub m, where m is some smaller permutation group, right. If I have 15 elements but I permute only 10, I am effectively looking at S10, not S15. So it will contain all kinds of other elements, but the particular embedding of a group of size n, when reflected as Sn acting on carrier space of size n, it necessarily picks out those elements from Sn which necessarily are category 1. So now we define what is called regular representation or regular permutations, I am sorry, are this category. So either the identity E which changes nothing at all, or only category 1 permutations. In which every element has to be touched and transformed into something else in the carrier space. This kind of permutations have one important property which it sort of, so this is a sufficient condition, not a necessary one, but the sufficient condition that these obey is that their cycle structure will come out to have cycles of exactly same size. Okay, so this is the theorem we are now trying to prove. Regular permutations in cycle notation will have cycles of equal length. So this is an interesting theorem to prove, and the proof goes something like this. So, suppose I have some group element G, so it is now of course represented through this pi. Suppose pi of G contains one cycle of length L1 and another cycle of length L2 and then whatever else there is, but suppose it contains two cycles of unequal length. But now the point is if I raise this pi G to power L1, then what will happen is that this cycle will have cycled through L times and will have returned to the original configuration. So it is equal to this, the first L1 in original config. But what happens to the others? So if L2 is an incompatible number or a larger number, so if L1 is 8, if L2 is 4, well you are lucky because it will also have cycled through enough times. But if L2 is 5 or is 59, then after doing power L1, L2 is not going to return to its original form. So you have reached a contradiction that you have two elements in the set pi G and pi G to the power L1 such that they share one cycle. But we already know that this is not possible unless the two elements are identical. You can't have some elements unchanged and some not changed and have two different elements, right? Because each element, so this, suppose we call this pi of GH, okay, some new element which is where H is actually G to the power L. So it will be represented by pi G to the power L right, it would be g to the power L1. So this is g to the power L1. Therefore, in the pi representation it will be represented by pi g to the power L1 because of homomorphism, multiplication property, right. So you understand that then these two elements pi g and pi h will share one cycle but not share the other cycles, but this is not possible because it will mean that their multiplication table row will share some elements but not share some other elements. But this is not possible because every row in this is unique. Okay. So there is a contradiction. So this is not necessarily in the same form. So then there are two elements, pi h not equal to pi g, but share one cycle. So this contradicts uniqueness of or the property of the category 1 property of uniqueness of G, multiplication table of G. You can think of it in two ways. Or you can think more correctly that it contradicts the category 1 property, that all objects have to be transformed, and the uniqueness is required. You do need the uniqueness property. Okay. So i.e. I will just say contradicts. It doesn't contradict category 1 property. Category 1 is a slightly more general thing. As we said, that is the sufficient condition. Yes. So what I have not fixed is the fact that all regular permutations, a set of regular, this is actually claimed for any regular permutation without checking that it is member of a group. But at least I have proved when the permutation is a member of a group G of size n, it is certainly true. In any case, this proof works. Even if I made a mistake in writing L1 instead of L1 plus 1, the fact remains that if the other cycles are not compatible with that length, then this you will get a non-unique representation. So what this is a very powerful theorem which says that when you embed an element of size n, a group of size n, into the permutation group or symmetric group, you will automatically get groups represented by elements represented by cycles of equal length. Okay. And the smallest example of this group of size 4, the C4, in C4, so consider C4, didn't we call it C4? Yes. So I have a square A, B, C, D, and I am basically considering pi by 2 rotations at a time. So 2 pi by 4 into n is the possible rotations. So let us draw the multiplication table, that is the simplest way. One can see probably geometrically, but I just find it easier to do this like this here just now. And this was the case in which basically B, so A is a pi by 2 rotation and B is a pi rotation. So what pi rotation did was to, its square was equal to identity, but the others did not square to identity. So A squared actually became B, 2 pi rotations becomes 2 pi by 2 rotations becomes a pi rotation. So A times A is actually B. Similarly, C times C also becomes B, because 3 pi by 2 rotation and another 3 pi by 2 rotation, so it becomes B. So this is essentially what the multiplication table is. So we got A, B, then I have to fill here C and I have to fill here E, because A and C are inverses of each other, 3 pi by 2 and pi by 2. So E here and A, so here I have to put a C and here I have to put B, sorry, A and A. Now let us write this out as cycles. So this of course is the identity element. This is written as, so now if we represent these, call this 1, 2 and 3. So let us write pi 1 according to rule we have devised, and then we look at the row of 1 which says A, B, C, E. Now how do we write this in cycle structure? E goes to A goes to B, B goes to C and C goes to E. So it is of the form E, A, B, C, but which is same as what we would have written in the 1, 2, 3, 4 notation, it is this. Next let us write pi 2. So what do we get with pi 2? It splits up into two cycles, two cycles. E goes to B, but B goes back to E. So there is an EB cycle, and then E goes to C, C goes to A. So there is another cycle. So in our note, we can write it. This is equivalent to first write the obviously visible EB, and then write AC. But it is also equal to, in our usual notation, 1, 2. Sorry, this we would have called 3, and 2 with 4, something like this. So it is now broken up into 2 cycles, but again 2 cycles of same size. Now a example of size 4 is not a very general one, but we do see that this is what happens. Either we get cycle of size 4 or we get 2 cycles of size 2. Okay, so we can just quickly check what happens. Can you check what happens to pi 3? Right, so it should be of this 4 cycle form. So similarly, pi 3 is also of, what is the cycle? 1, 1, 4, 3, 2. Okay. So we got cycles of equal size. Now this is a very important, similarly I can tell you right away, if you do the other order 4 group, the Klein group, which if you remember had E along the whole diagonal, Klein group will produce all pairs, 2 cycle pairs. It will have no 4 cycle in it. So you can check that. Let us try to write it in table form and then see what we get. So check this particular, so regular permutation. I am not completely sure, so I will just check it in front of you. So I have 1, 2, 3 and then 4, 5. In the usual notation, we will write it out as 1, 2, 3, 4, 5, and it will become, because 1 goes to 2, 2 goes to 3, 3 goes to 1 and 5, 4. So yeah, I don't think there is anything wrong with this, satisfies the criteria. Satisfies the proposed property, okay. But what we will now, so I think I have to restrict myself to we will consider embedding of a group size in Sn through pi. Then for that these facts are correct. As you know, I had to here, I was about to write and then I didn't write. So this is verified for all the regular permutations that occur in representing a group. So at least checked for, so proved for which belong to a group G, okay, with G of that or mod G equal to n. Because if G has to, if the set of these regular permutations have to become elements of G, then this multiplication table restriction is a powerful one, that each row has to be unique. So what will happen is that this particular thing that we checked will not square to the, will not represent any group element. Will not occur in any group of order 5. That much I can guarantee you, because you take any group of order 5 and try to embed it in this, it will this will necessarily this argument will then apply, that I have incompatible cycles. So if I took this and just squared it, I do this and then I do it once again, these two will come back to themselves, but this 1, 2, 3 cycle will not have completed. So it will amount to having 2 distinct elements in this table whose 2 of the elements remain same while the other 3 are not same. So it will not be a unique representation. And here the argument is quite watertight, that you know from basic axioms of group theory, it is impossible to have any repeated element in any row, and it is impossible to have any 2 rows having any identical element in any column, because then it means one of the elements is identity. The way we define by just requiring that every element is touched is a little too generic. That is the broader property, but conversely a group of size n when embedded in pi n will necessarily be represented by regular representations, but it does not mean that every regular representation will occur in a group. Okay. As I said, the word regular by itself does not register as what are the properties it captures. So, there are nomenclature problems. But as far as you, so long as you try to embed a group of size n into Sn, you will find that these properties are correct, that it has to break up into any cycle representation will be cycles of equal numbers. And in fact, that brings us to the interesting point that at least for small size groups where you do not have some n factorial to worry about, but up to 5, 6 size groups, you can in fact deduce all possible groups by this requirement in reverse. Because if you want to write a group of size 5, you are forced to have only one group, because you can't break up 5 into equal cycles.